well as head of department, Dr. Bhusan, for inviting me here. And I'm going to present something related to microwave assisted compression molding. So basically, I am Nishan Sharma, and after completing my PhD from Indian Institute of Technology, Mandi, I have been a part of Hindustan Petroleum Corporation Limited. After that, I joined Vijay Product Limited. Now I am working as an design and development engineer at Medora Meditech Private Limited. So Medora Meditech is the medical device manufacturing company, and we are manufacturing more than 50 basically our specialization is on the stunt. So we are manufacturing self-expandable metallic stunt covered as well as uncovered, and we are manufacturer of stone retrieval basket, stone extraction balloon, endoscopic accessories, and electrosurgical knife, US needle, and foreign body management. Today I'm presenting microwave assisted compression molding technique. It is a very new technique, and it has many advantages compared to the conventional manufacturing technique. As you know, the how much polymer composite, how much important are there. It is used in the aerospace industry as well as the domestic household industry and the automotive industry. So in order to avoid the various defects during manufacturing, this new technique can be used to develop the polymer composite. So these are my presentation on outline. I would start from the introduction of composite material classification and primary manufacturing technique. Then I would explain the mechanism of microwave heating and fabrication of particulate reinforced composite and fiber reinforced composite as well. So first of all, I would like to introduce about the composite material. So hope you already know about the basic of composite material. So composite material is nothing but it is the mixture or combination of material. But one thing is very important: the two material is physically mixed in each other. They should not chemically combine, or they should not form any chemical bond. They should be insoluble in each other. So this is the things that we should remember during the fabrication of composite, because two terms are there. One is the interface, other one is the phase. So the two materials should not be chemical combined in each other. So there are several advantages of composite. They are low cost. These all are theoretical advantages: low cost, lightweight, high specific stiffness. These all advantages are presented in Google as well as in the books. So this is the classification of polymer matrix composite. These polymer matrix composite are classified based on the matrix and based on the reinforcement. So based on the matrix material, the thermal and thermosetting kind of matrices are there. So hope you already know about the difference between thermoplastic and thermosetting. Can anybody tell the difference between thermoplastic and thermosetting? Hello, am I audible?
Yes, sir. You are audible, sir.
Hello. Okay. So can anybody tell? Okay, okay, sir. Okay. So basically, thermoplastic polymers are those which melt on heating, while thermosetting polymer are those which cure on heating. Cure means which get cross-linked on heating, and thermoplastic polymer can be reshape again and again under effect of heating. While in case of thermosetting polymer, once it gets solidify, if we apply more heat, then there is a degradation. So these are basic difference between thermoplastic and thermosetting polymer. And based on reinforcement, the composite are classified fiber reinforced polymer and particulate reinforced polymer. The particulate reinforced polymer composite are classified in random orientation, because the orientation in case of particulate reinforced as well as fiber reinforcement polymer is very important. So sometime it is randomly oriented, or sometime it is systematically oriented. So in case of fiber reinforced, there is single layer fiber reinforced composite as well as the multi-layer fiber reinforced composite. In case of single layer, there are long and continuous fiber, while uh, and other one is the short and discontinuous fiber. So fiber are also classified as unidirectional as well as bidirectional fiber. So the mechanical response of the composite is totally dependent on the which kind of particulate you are using, and which kind of fiber you are using, what is the orientation of fiber, what is the distribution of fiber, either it is oriented 0 90 0 45 0 0 90 90. So this way the mechanical response of the composite majorly dependent on how we are processing the polymer, and how what kind of reinforcement we are using, what is the strength of reinforcement, what is the aspect ratio of reinforcement. So these all are dependent factor for the mechanical response of the composite material. So in case of multi-layer composite, there is laminated as well as the hybrid laminated kind of uh, fiber reinforced composite is there. So I already explained the key factor which determine the mechanical behavior of composite. One is the fiber size, fiber orientation and distribution, processing route, matrix fiber adhesion, and fiber concentration. So in this point we can see that processing route is also very important. How you are processing the polymer composite, the resultant mechanical properties are dependent on that also. So there are several processing routes for the polymer as well as the composite. So in case of thermoplastic, we can apply the direct pressure to the uh, matrix material, while in case of thermosetting, as you already know, the thermosetting kind of polymer, the raw material mostly comes in the form of resin. So how anyone can apply the direct pressure on it? So indirect kind of pressure is required. So how indirect pressure can be applied? Either by gas pressure or by the vacuum pressure, while in case of thermoplastic polymer, the direct pressure can be applied. So after that, I would directly come on that new area, that is microwave assisted compression molding. I would not explain the conventional technique. This technique I would explain. In case of conventional heating and microwave heating, both heating procedure and heating mechanism are different. In case of conventional heating, the heat transfer occurs from the surface to core. From surface to core. Most of the time you have observed a thing that suppose you have kept a container of water on the stove. Sometime you observe that the upper layer of that water is hot, and the lower bottom layer water is cold. How this happen? This happen because of the thermal gradient, and the heat transfer from hotter region to colder region. This is the conventional heating transfer phenomena. While in case of microwave heating, the molecule of the material interact with the microwave. First thing, molecule of the material interact with the microwave. After that, some oscillation will takes place in that molecule, and due to that oscillation, some kinetic energy will produce. Kinetic energy will transform into heat energy. So in case of conventional heating, heat transfer takes place, while in case of microwave heating, the heat conversion takes place. Heat conversion from wave to the heat, or we can say electromagnetic wave to the heat. Due to this phenomena, we have a lot of advantages like volumetric heating
Kayak lecture
uh,
ini oh,
and
kan
the
ikin di.
hello. Any question? Hello, hello
Speed,
audience.
speed.
Any question?
हाँ. Hmm. अच्छा. যদি 1 মার্ক আসতা
Uh,
ঠিক ଅଛି. যে
question
3
till
মার্ক
now,
ଆସିଗଲା
audience.
ଏଇଟା ହବନି. ଏଇଟା କୋଉଟା ବନା ହେଲା? ଏଇଟା
So
ୱାଲ.
okay.
କାନ୍ଥଟା ବନା ହେଇକି ଥାଇଛି ହେଲା.
So
3
these are
ମାର୍କ ହେଲେ
the
କଣ ଲେଖିବ?
advantages of
ଗୋଟେ ହେଲେ
microwave
ଶୁଣ
heating:
ଗୋଟେ ଡୋର ଲେଖିବ, ଗୋଟେ
cost
ୱିଣ୍ଡୋ.
saving, low cost equipment, volumetric and selective heating, and environment friendly, precise heating control in quality and property. So microwave is well known for the rapid heating. So if heating is rapid, then it's quite obvious that it has the property of cost saving, right? So till now, these are some material which already explored in the microwave processing of material. So microwave can process the ceramic as well as the metal and polymer, everything it can process. But the how user is using the microwave, that also matters. Sometime we can use the direct heating. Sometime we have to use the indirect heating. Indirect heating means heat the susceptor and transfer the heat to the contact material. So this animation you can see that I will explain. Firstly, the microwave would come and it would interact with the molecule of the material. And after interacting the molecule of material, some electromagnetic waves are there, and that electromagnetic waves will oscillate the dipole and it will transform the microwaves into heat. So this is the thing. So two mechanisms are there. One is the polarization and another one is the ionic conduction. So how different material interact with the microwave? So sometimes microwave transparent materials are there, microwave opaque material, microwave absorber material, mixed absorber material. So microwave interact with material selectively, as I already discussed: selective heating, volumetric heating, and rapid heating. These three are the main property of the microwave: rapid, volumetric, and intensive heating. So in case of microwave transparent material, so what are the microwave transparent material which allow microwave passing through them throughout the thickness? So these are the microwave transparent material. These are Teflon, quartz. And in the further slide, I will explain how we have make the use of these transparent, opaque, and absorber material for the this making of the composite. So microwave transparent material, Teflon and quartz. Microwave opaque material are the all bulk metal. Due to lower skin depth, the all bulk metal are microwave opaque. And microwave absorber material are water, silicon carbide, charcoal. And another category is mixed absorber. Mixed absorber are composite. So in case of composite, sometimes the matrix is microwave absorbing material and sometimes the reinforcement is microwave absorbing material. In case of whenever the reinforcement is microwave absorbing material, the microwave will directly interact with the reinforcement and it will transfer heat to the matrix material. So this is the theory of microwave curing in the composite. Basically, two factors are wait. Basically, generally two factors are responsible for the microwave heating. One is the dielectric constant factor, second is the dielectric loss factor. So generally the complex permittivity depends upon both the factor, and the temperature dependent relaxation is the exponential function of the electromagnetic waves. After that, the heat is produced. Heat is the function of again dielectric constant and dielectric loss factor, as well as the produced electrical field. So in case of non-magnetic field, non-magnetic material, the magnetic component of the field has been cancelled out, and only electric field is responsible for the microwave heating. So basically, now I would say how we have manufactured the particulate reinforced composite by the microwave energy. As in the slide you can see that there are particle of matrix as well as the reinforcement. So reinforcement is the hydroxyapatite, because we have used the hydroxyapatite for the biomedical applications. So one is one we seen the scanning electron microscopy of ultra high molecular weight polyethylene. It is in the powder form, and the nanohydroxyapatite is also in the form of powder. So how we have make the use of the microwave transparent material to heat the microwave and to maximize the consumption of microwave for the heating. In this figure you can see the dead weight. Dead weight is used to apply the pressure, and you can see the IR pyrometer is used to measure the temperature. Why we need to measure the temperature? Because we need to process the polymer just slightly before the melting point. And how we can determine the melting point of polymer? Anyone from audience? How we can determine? Hello? Is anyone having any idea about how we can determine the melting point of the known polymer? Hello, am I audible, sir?
Yes, sir.
Okay. So this is the dead weight. This we have applied to concentrate the pressure in matrix as well as the reinforcement. These are the powder particle, powder of ultra high molecular weight polyethylene and the nanohydroxyapatite. These are the microwaves, and alumina tape we have used to seal this, because alumina is microwave reflecting material, and it didn't allow to pass the microwave throughout the thickness. So it will reflect back the microwave and concentrate here. So we have two material, matrix and reinforcement. So in this way the ultra high molecular weight polyethylene and nanohydroxyapatite is arranged. After, whenever the microwave is came, what happened? It directly interact with the nanohydroxyapatite, and as well as it interact with the ultra high molecular weight polyethylene powder. So but it interact more with the nanohydroxyapatite. Why? Because the dielectric constant value of nanohydroxyapatite is greater compared to the ultra high molecular weight polyethylene. So firstly these particle would heat, would transfer their heat to the surrounding material, and with the application of 0.02 megapascal load, this load we have optimized by trial and error. So it this load was sufficient to decrease the porosity. In this figure from the SAM, you can see the higher porosity without the effect of pressure. But after applying the pressure of 2 megapascal, the dense polymer we have attained, and we can see the scanning electron micrograph of this material. These are the temperature time curve for the high molecular weight polyethylene and 10% nanohydroxyapatite, 15% nanohydroxyapatite, and 20% nanohydroxyapatite. So we can see the temperature time curve for this material, this material, and this material. So we can see that the temperature same the temperature reach in 1600 in case of neat ultra high molecular weight polyethylene, while in poly composite it attained that temperature in 800 Why? Because we are introducing that particle which having higher dielectric constant value, and that more with the microwave energy. That's why this thing. And another category we have used to this microwave assisted compression molding to develop the polycaprolactone based composite, and we have produced the foam. How we have done? Again, we have taken the alumina mold. Why we have taken the alumina mold? Because alumina is a microwave transparent material, and it is thermally stable up to 8 to 900 degrees Celsius. While in case of polymer, we only matter up to 150 or 200 degrees Celsius, but it is very stable. And second thing is there, it allow the microwave passing. So we have put the raw material contain polycaprolactone, nanohydroxyapatite, and salt. We have induced all the things in this mold, and we have put this mold under the microwave. So what mechanism is happens in case of these three material? The NaCl, that is salt has higher dielectric constant compared to the polycaprolactone and nanohydroxyapatite. So firstly, the heat transfer would takes from the that NaCl to hydroxyapatite, then to pellet. And after fabrication, we have done the leaching. Why we have done the leaching? Because we have dissolved the salt particle, and after dissolving the salt particle, the pores are generated. Whenever the salt particles are attached on the material, at that place the pores are generated. And interesting thing is that the pore size is exactly equal to the particle size of the NaCl. So these are the all about the PCl nanohydroxyapatite composite. So in that, again in the temperature time curve, we can see that in case of pure PCl polycaprolactone, and in case of composite, and in case of the material where the NaCl was there, so you can see the that temperature time curve. So how rapidly it is heated in case of polycaprolactone? So these all data has is already published by us in several journal articles. So after that, we have made the composite. Now the biocompatibility is the main property. Whenever you need to claim the composite whether it is biocompatible or not, we need to check its biocompatibility. There are several ways to assess the biocompatibility: in vivo, in vitro. So in vitro done in the laboratory level, in vivo done on the animal, and after that the clinical trials are there, FDA regulations are there. There are a lot of things in the medical regulatory. So we have done the indirect contact say assessment test with the collaboration of some other lab, because as you already know, I am from mechanical background, and these cell kind of things I am not much aware, but something that I have learned. So firstly, we have done the Delvaco modified Eagle media with the phosphate buffer saline solution. So we have supplemented these all cell with the bovine serum, so cell should not kill with the deficiency of nutrient. So basic thing is that cells can be killed with the contact of material, but it should not kill with the that deficiency of nutrient. So we have supplemented with the bovine serum, and after that we have put the amino solution, and this converted into the live chromatin crystal. And live chromatin crystal we have dissolved in the 100 microliter DMS dimethyl sulfate oxide, and after that we have done the optical density measurement. The principle is that higher the optical density measurement value, higher the cell viability. So we can see the cell viability here in the microscope. So in this case, we can see the cell viability. So all the specimen support the cell viability and cell proliferation. After that, we have done the another test that is known as hemocompatibility. So hemocompatibility refers to evaluate the biomaterial under the contact of blood. So by taking the blood from the volunteer, after taking the approval from ethical committee, we have taken the blood from the healthy volunteer, and we have centrifuged the blood at 100 rpm and dilute it with the phosphate buffer saline solution. And after that we evaluate the blood content by maintaining the positive control and negative control. So we have separated the blood content. So RBC we have separated, and PBMC. PBMC is the peripherally blood mononuclear cell. It is the most abundant white blood cell. So our specimens pass non-hemocompatible nature, as well as it also support the growth of PBMC. And after that, we have done the platelet adhesion test, and the pseudopodia can be seen in the specimen. So after that, once we have made the composite material, now it is very important to assess the bond bonding ability of the material, because otherwise it would get delaminated from the natural bone. So material have the bond bonding ability, because it should naturally grow under the presence of bone, otherwise it will get delaminated. So in order to find this thing, the material should have the prone to formation of apatite crystal. So we have done the simulated body fluid. See, it is synthetic, and we can see in the say that industrial. And we have immersed the specimen in that fluid, and after a certain days, like the 14 days and 21 days, we can see that the material have the bone bonding ability. So in this slide, I would explain how the fiber reinforced composite can be manufactured by the same technique, that is microwave heating. So this phenomena I already explained, that how the molecular interactions takes place in this microwave, and how the dipole interaction, and how the oscillation takes place, and which convert the microwave energy into the heat. So as I already explained, two phenomena occurs. In first case, the reinforcement may be the microwave absorbing material, and polymer is a microwave transparent material. In another case, the reinforcement might be the microwave transparent material, and polymer may be the microwave absorbing material. So dielectric constant of whenever the case, the dielectric constant of the fiber is higher, the microwave will interact with fiber at the higher rate compared to the matrix material. So this is the experimental setup for in case of fiber reinforced composite. So we have placed the sheet of polymer, and after that sheet, or we can also place the pellets. After that we can place the fiber and again pellet. In this way we can make the sandwich structure, and we have used the dead weight to generate the force on the mold. This is the pressure plate. The whole mold is covered with the that, and fiber mat as well as the matrix can be visible in the slides. So as I already explained, what would happen if microwave is if fiber is microwave transparent, it would interact with the microwave rapidly compared to the matrix material, and it would start hitting first. So these are the exposure time and pressure that, and we can see the temperature time curve for the same thing, that is PP based composite and PE based composite. So in this case we are at this stage we are switching off the microwave and power takes place, and up to this reason we have hit the sandwich. So these are the something that we have optimized the microwave power. So generally the industry microwave power, or in case of domestic microwave power, you can see that there are multiple level: 360, 500, 520, 900, and how we are optimized this. So in case of 360 microwave power, the instant microwave interaction takes place and no melting. And the some otherwise we can heat up to the longer time, but that thing is not feasible. So in case of 999 PP sheet melt and curing is incomplete. When we have increased the time to 1500, the complete curing of matrix takes place. And in case of 1800, the PP sheets overheated and burned in case of microwave. So in this way we have optimized the thing. So this is very important. So we have made the microwave assisted compression molding compatible with the industrial process, because conventional compression molding is widely accepted in the industry. So how microwave can find their place in the industry, because every industry people are prefer only the conventional compression molding. So these thing we need to prove. Whenever we have read the manuscript, the reviewer asked a very good question. So reviewer asked, what reviewer asked? Reviewer asked, is this technique is relevant to industry, or it is only on the laboratory level? So that time we did not explore this thing, but suddenly our mind strikes, and we have analyzed that if we are making something, that it should be also useful for the industry, and there should be the solder to solder comparison of the conventional compression molding and microwave assisted compression molding. So what we did, this is the setup of this is the laboratory level setup of the conventional compression molding, but it was sufficient to prove our study. This is the top plate, bottom plate, hydraulic plunger, whole things are made to make the composite. What we have done, we have take the polymer sheets as well as the fiber sheets, and we have taken the thermocouple, and we induce the thermocouple between two polymer sheet, two fiber sheet, and bottom one again in case of the polymer sheet. And in similar things we have replicate on the microwave. In case of microwave, get in case of microwave assisted compression molding, we can see that to 200 seconds, while in case of microwave heating, similar temperature achieved in 400 seconds. And in case of temperature gradient, this is the thermal image of the microwave assisted compression molding, and this is the conventional compression molding. So we can see that how some spots are there. So from this temperature, we can see temperature and specimen length. We can see the how much variation in case of conventional compression molding, while in case of microwave assisted compression molding, the heat is very uniform throughout the specimen. We have done the also validate this thing by using the thermocouple. We have put the thermocouple at different length of the specimen and prove our study. And this also proved the mechanism that I already explained. What happened in case of the conventional compression molding? These are the matrix layer, these are the fiber layer, and the heat transfer takes place from the surface to the core. This surface is connected with the bottom and top plate of the conventional compression molding, and it transfer their heat from the matrix to fiber, and again the sandwich and that fabrication takes place. While in case of microwave assisted compression molding, the heat is interacted with the fiber, and after interaction it would transfer their heat to the matrix material. In this way the fusion takes place. So in this way we have done this study, and in case of mechanical response, we also analyzed the mechanical response, and we can see that the mechanical response of the microwave assisted compression molding is far better compared to the conventional compression molding. This all are about the thermoplastic based composite. Now we would explain the application of microwave during thermosetting. So one thing I already explained, that direct pressure cannot be applied in case of thermosetting. Why? Because most of the thermosettings comes in the form of resin or liquid. So how anyone can apply the direct pressure? So generally some studies are there, hand layup, wet layup, in which the direct pressure has been applied. But generally it is not recommended to apply the direct pressure on the thermosetting matrix, in order to avoid the damage, as well as the to in order to make the composite. It is not recommended, or it is less recommended to use the direct pressure in case of thermosetting matrix. So how we have made the arrangement of this thing in case of microwave? What we have done, we have one side we have taken a vacuum pump in order to make the vacuum pressure, and some laminates are there, fiber laminates, and after switch on the microwave, it start curing the that polymer, that either epoxy or other kind of thermosetting polymer. So these are the resin tanks, and these are the data acquisition system. Earlier we have used by the thermocouple and thermal imaging camera, and this
ఇది
is the PTFE mode.
నేను
Why
జవాబు నేను
PTFE
అసలు
mode?
వింటున్నా
Hello. Any question, sir? Hello. Okay, okay, thank you. So this is the pressure gauge. Why pressure gauge is required? Because we also need to quantify the vacuum pressure. So, and also we need to optimize the vacuum pressure, because the behavior of composite, or the manufacturing of composite differs in case of the whenever the lower vacuum pressure and whenever the higher vacuum pressure. And this IR thermal imaging is used to quantify the temperature. So why temperature monitoring is important? Because we have something term called glass transition, transition temperature, or a curing temperature. So we need to heat till the achievement of that temperature. So after the solidification of this thing, the vacuum bagging film has been peel out, and the specimen can be made. So similar technique of temperature measurement we have used in this technique also. So this I already explained how the microwave is interacted with the fiber as well as the epoxy. So the dipole moment takes place whenever the microwaves comes and interact with the material. Some oscillation takes place, and due to that oscillation, some heat will produce, and resultant the curing of polymer takes place. So we also analyzed the time consumption and energy consumption, whether in case of microwave assisted vacuum resin molding, and in case of the conventional. So here we have taken the microwave power at 180 watt, 360 watt, 540 watt, and 720 watt. And you can see that how much less time consumption in case of the microwave whenever we have used the conventional heating technique. How much times are there? 500, 5000 second around. And in this case the 3500, whenever we have taken the temperature of this 1000 as well as the 2000 in and other ordinary furnace. So these are some challenges associated with the microwave material processing. So it hitting low loss, poorly absorbing materials such as the bulk metal. As I already explained, it is not useful to heat the metals due to the low skin depth. So direct microwave heating cannot be used in case of the bulk metal. What we can done in that case, we can use the susceptor heating. Susceptor is the like charcoal. So we can take the heating from the charcoal to the bulk metal, because we cannot heat directly the bulk metal inside the microwave. And in your house you already, I think you already seen that it is not recommended to use the metal utensils in the microwave, because it will create spark due to low skin depth. So how we can process the bulk metal? We can use the indirect heating. We can use that susceptor based heating to heat the charcoal, and from charcoal it can directly heat the that material. And after heating, and other the inverted thermal profile is not possible to visualize, because the upper layer it is easy to visualize, but the lower layer it is not easy to visualize in case of the microwave. And all material are not microwave tolerant, and not every material can be processed through the same technique. So this can be done in the future, because of scepter based heating, separator based heating, mask, these kind of application we can use it. And in case of tooling we can use the gas pressure, liquid pressure, this kind of flexible kind of design we can use in the target material. As I already explained, polymer matrix composite are easy to process this technique, but high temperature ceramics and high temperature alloys, that are not easy to process by this kind of technique. So these are some future scope to process this material. The modeling can be done, and in process physical interaction can be done, and the design Hello audience, any question? Oh, voice is break. Okay, okay, wait. So voice is breaking. Wait. Okay, so if someone have any question, then you are most welcome to ask, related to this work or some other kind of things related to medical devices and related to how industry work in case of launching the medical devices. If someone have any question, then you are most welcome to ask. Am I audible, sir? Hello. Okay.
Sir, good morning. Good evening, sir. My name is Vijay Mohan.
Yes, sir. Tell.
Sir, I have a few questions regarding the type of mold that we can use. Can you give some examples of
Okay.
different forms of material molds that we can use in this method? So you
Okay,
specifically
sir.
mentioned we
It
are
is
using
very nice question.
aluminum.
Yes, we are using alumina. So in order to select the mold, we should careful about the certain factor. First factor, the mold should be microwave transparent, because if it would not be microwave transparent, then either it will absorb the heat, absorb the microwaves, or it will reflect back the microwave. So first condition is there, the mold should be microwave transparent. Now second condition, the second condition is it should sustain the temperature, the processing temperature. Suppose you are using high density polyethylene, so the melting point of high density polyethylene is around about 120 or 125 degrees Celsius. So if you are using the material which can sustain 250 or 350 degrees Celsius, that is sufficient. Or most of the time you need to choose the material which is thermally stable and microwave transparent. So till now we have used the two mold. One is made up of alumina, that is screen visible?
Yes, sir.
Hello,
Yes, sir. It is visible.
is visible. So till now we have used the alumina mold, and in case of thermosetting polymer, we have used the PTFE mold. Why PTFE? Because in case of thermosetting polymer, sometime it might be sticky. So in order to avoid that sticky phenomena, we can choose mold in that way. So till now we have used only two mold. One is the alumina and another one is the PTFE mold. PTFE you can easily take and machine. We have taken the alumina from, there is a company in Chennai, Ant Ceramic karke. So you can directly procure the mold from there.
Thank you, sir. Thank you so much.
And whenever you are processing the metal, some other kind of molds can be used like zirconia, which can sustain the higher temperature. So this is all about the mold.
Sir, one another query. Sir,
Yes, yes.
is the in the image you are showing a microwave assisted mold and the complete setup that you have shown here. Sir, is
Yes.
it industrial purpose or is it specifically designed for your purpose of
Uh,
use, sir?
yes, that time during my PhD, we have designed it for our only lab work. But when I was about to complete my PhD, we got some patent, and we have also means some technology transfer. That kind of things are going with the industry. Now we are able to produce the component of 1 feet, 1 square feet. So if your requirement fit in that constraint, then yes, it is suitable for the industry. But beyond 1 feet, it is again producing some hotspot, and we cannot able to process the uh, job of that dimension more than 1 square feet, because it is producing some hotspot. So currently we cannot fully claim that it is useful for industrial purpose, but yes, we can say that it is in the transient stage. We are doing some technology transfer kind of work for this particular setup. Why? Because it have the property that I already mentioned. It have the property of the intensive heating, volumetric heating, and some temperature gradient that I already shown in my slides. So in case of conventional heating, wait, let me go on that slide. So see this slide. This figure A, this is the thermal profile by microwave assisted compression molding, and this is by conventional compression molding, and it is the temperature time curve of microwave assisted compression molding, and it is the conventional compression molding. So I think you can observe the advantage, how rapidly it can heat the same volume of the material, and with lesser defects. And we also analyze the mechanical response. In case of mechanical response, it did not able to contribute increase in the Young's modulus, but yes, it is the mechanical response in terms of ultimate tensile strength, flexural strength. The mechanical response is far better in case of microwave assisted compression molding compared to the conventional compression molding. And whenever you are heating, so suppose in case of conventional compression molding, this area is overheating, then definitely it will produce some defects on this particular area. Not that much contribute in the mechanical response, but yes, in case of microwave assisted compression, uniform heating is there. We have proved this thing by our setup.
Sir, one another last query. Can we have your number and mail if there is any further assistance needed?
Yes, yes. I would tell the professor Asit. He will share my mail ID as well as my contact number. Well, I'm writing my contact number here, so you can WhatsApp your query. So if any questions related to the medical device and how the industry work, that also you can ask, means not related to this slide, but you can ask other query also. So I have pinned my number. Any other question?
Thank you, sir. Thank you so much, sir.
Any other question from other audience? Okay, sir. So this is all about my presentation. So I'm going to conclude my slides here. So thank you. It was very wonderful interaction, and I'm very grateful to you, as well as the other organizing committee. So you give me the chance to speak here in front of you. So thank you. Yes, we have a time. So my only motive to make this session more interactive. So I want that audience would ask more and more questions related to anything related to medical devices, as well as from this technique. Yes, 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 sir, please. Uh, uh, means microwave assisted compression molding. Till now, sir, some industries came with us, and some technology transfer kind of work is going on. But till now, that thing not successful. But yes, in case of thermosetting polymer, NAL, National Aerospace Laboratory, they are making some aerospace kind of research, and that another company Boeing, they are going to implement this on the large scale. Like we have also collaborator in the National Aerospace Laboratory, that is scientist Rao. So they have done a lot of work on this technique, that this microwave assisted not compression molding, that other that I explain, vacuum assisted resin transfer molding. So they are means it is commercially it is this of thermosetting polymer commercially. But in case of thermoplasting polymer, it is not using till now. And even we are the first group in India who reported this thing. So some question is there in the chat box. For Stunt India product not given, not much giving import. Could you share the reason? Yes, so actually the stunt manufacturer in India is lesser, and most of the means earlier before 2016, all stunts were imported. Even the act, firstly the medical devices was covered under the act of cosmetic acts, but in 2017 the medical device act came into the picture, and most of the manufacturer are focused to develop the medical device in India, and government is also focused to decrease the export from the outside. And yes, trust is the main issue, because this is the new field in the India. Earlier, because all the stunts were imported from the major manufacturer, Boston Scientific, Stryker. So these all are the US brand. But after getting the Medical Device Act in India, so people are getting the acceptability. And if you analyze the market share from 2017 to till now, the market share of Indian manufacturer are rapidly rising. And today uh, the Indian manufacturer also covering more than 40% market share. So this proves the huge acceptability of the means Indian manufacturer. Any other? Yes, sir. In case, okay, in case of larger specimen, suppose specimen is more than 300 or 30 centimeter, or you can see say that 1 feet. So some hotspots are formed on the composite, because in case of microwave, domestic microwave, you have seen there is a rotating plate. So rotating plate is used to uniform the microwave to the specimen or food. So but in case of that commercial microwave setup, some stirrer are there specimen. But I don't know why in the case of larger specimen, more than 1 feet specimen, some hot spots are formed on the surface. This may be due to the uniformity of that microwave, because microwave are not uniformly interacting with the material. So this is hypothesis. I don't have the practical evidence for that. So it might be the reason. Yes, yes. Sir, it is possible to join thermosetting and thermoplastic material can be joined together. So in this case, joining, I'm not sure about the joining, which kind of joining you are asking. If you are asking about the joining through welding or fusion, then I think it is possible. But if you want to induce thermoplastic in thermosetting polymer, that is also possible. But you can take the thermosetting resin, and you can mix the thermoplastic powder. But remember, the thermoplastic material should be in the form of powder, and you can stir that and you can cure that kind of things you can doing, but still some delamination kind of things would come in that. So these are the two way that we can try, and we can learn from the explore how we can do. But these are two way. One, we can induce the thermoplastic material inside thermosetting resin, and mix that. After that we can cure the thermosetting resin. So, and in other case, if you are asking about the weldability of the two plates, then we can take the thermosetting as well as the thermoplastic, and we can join, because it is the, I think, low temperature processing material. So this thing can be done. I didn't try this, but as far of my experience, I can able to answer this.
Sir, Vimal sir, hello.
Hello.
Sir, is my voice audible, sir?
So yes, audible.
Yeah. Sir, I have one doubt regarding when you show us the challenges that to be addressed. So,
Yes, yes.
can you give some a light to this thing on thermal run? How to control the thermal run while dealing with large metals?
Sorry, large.
Large metals, material.
Large metal, or means you are talking about the large dimensions material, or metal?
Large dimension material. Sorry, large dimension materials.
Okay, in case of large dimension material, because we already tried to equalize the that or so that the microwave should uniformly interacted with the material. Some stirrer can be used, but we already used that stirrer, but it was not useful. So this is the new area that means I am also exploring these things, how it can be done. But till now I don't have the clarity so that I can answer this query. But one thing that I have clear, that the microwave should be uniformly interacted with the material, either it is large or it is small. So what how or what steps can be taken so that we can uniformly distribute that micro, because these are the waves and we cannot see them. So if we cannot see them, then how we can but resultant we can take the thermal image and we can see the hot spot. And if you are doing something, or you are doing some experiment, so you can easily detect by that thermal imaging, or that other thermocouples.
Okay, sir, if I want to see through thermal image and I want to make it as a AI model, for thermal imager, what should be the temperature range I have to look for the thermal image camera? If I want to
Can you
conduct
repeat? Can you repeat your question? I am not able to understand. You are taking
the,
some thermal
yeah,
data points, right?
yeah, thermal data points to control the process. So based upon the
Okay,
thermal image cameras using AI models. So for the
okay.
thermal image camera setup, what should be the temperature range I have to look after? Because we have certain range of temperatures which are provided by Flyer, Fluke, different companies are there, Metravi, like that.
Okay, it is very nice question actually. So the question is what temperature you should take.
Yeah.
So it depends upon what type of material you are processing. So whenever you are processing something in microwave, or whenever you are making the polymer composite, the processing temperature should be lesser than the melting temperature. Why it
Okay.
should be melting temperature? Because on the melting stage all the bonds get break, and it degrades the mechanical performance, because it starts the second cycle of heating. So most of the time it is recommended to take the DSC, differential scanning calorimetry value. From that we can analyze the melting point. and you need to take the temperature slightly before that melting point so that it is processed, but the bond should not be break.
Okay.
So yeah, this is the thing. It depends on the material to material. So you can take the value and you can model that kind of thing, and you can take the various machine learning model. There are, I forget the name, and you can model the
Yeah.
thermal.
Yeah. Okay. Thank you very much, sir.
Thank you. Okay. So in that case, one thing. So in my slide, in one slide I have mentioned at the 360 watt the fusion was not sufficient, while in case of 900 watt to certain times the overheating takes place. So what we can do, if somehow we can take the feedback value from the because we have the temperature value, and somehow we can control the controller of microwave through that value. Adaptive control can be made through the machine learning. So adaptive control, so that it can learn from the thermal profile, and in that way that it control the microwave power automatically. So this can be done either by means image reading, or we can done by the that data reading. So image processing can be done so that it can overcome the real time challenge. It is a very nice area to study. What technology advancement could further improve the microwave assisted compression molding? So one thing is most challenging. If that thing can be do, then it will rise the acceptability of microwave processing in the industry. That challenge I already mentioned, that it could not process the object of larger dimension. So you need to limit your area up to 1 feet only. But if somehow we can improve this, then it I can say it would be very useful for the industry, because somehow it is reducing the processing time and reducing the processing defect. But it is the main area which decrease the commercialization probability of this setup. So this thing can be used, and how we can use how we can do this thing, that I also don't know about the thing. In general, microwave heating is from so Professor Rao, is it clear to you? So if you have any question, then you can WhatsApp me. I already given my number. Next question from the Professor Bansal sir. In general, microwave heating is from inward toward outward. Then how? Yes, it is very nice question. Even most of the time reviewer also ask this question. So it is, yes, it is. I accept that it is the inward toward outward. But one more term that I explain, in case of microwave heating, the molecular interactions takes place. And in case of molecular interactions, the material have certain dielectric constant value. So whenever the microwaves comes, the all the molecules in the material interacts equally with that microwave. So So in this way, the uniform heating takes place. In case of why this question came inward toward outward, because the microwave has certain assume that it interact firstly with the core of the means the molecule which are presented at the core, but same time it also interacted with different material, because whenever concentrated, it firstly interacted with. Hello. Yes, sir. So this thing is already explained that through certain setup, it is well proved that it is uniform heating. Regarding this answer, I can say that the molecular is interacted equally at every place. But in case of microwave, the microwave firstly concentrated on the center. That's why this kind of gradient will form. But gradient is quite lesser compared to the conventional heating. Because in our setup also, you can see that the gradient is available. Wait, I will show that slide.
Yes, sir. Good evening, sir. So, Dr. Bansal here.
So
Sir, I read.
yes, sir. So
Yes,
uh,
yes, sir. Sir, I read
in
somewhere
the
that there is one term
yes,
like hybrid heating type, which can lower the thermal gradient. So,
yes,
in your case, are you also using the hybrid heating technique or the simple microwave heating?
no, we are
Because it
using
is
direct
not.
heating. In
Yes, sir.
yes,
Sorry, sir.
we are
Sorry. Sir, because it is not
okay. No
possible
issue.
to achieve the uniform heating through simple microwave heating, although we can achieve the uniform heating through microwave hybrid heating.
Okay, Bansal. So are you able to see this slide?
Yes, sir. Yes. I'm able to see, sir.
So in this slide, we can see that in case of conventional compression heating, there are data points throughout the length, and how much
Sir.
difference is there, you can see. While in case
Yes.
of microwave assisted compression molding, I can't say that there is uniform, but you can see the difference. Regarding your question related to microwave hybrid heating, so in
Yes, sir.
case of microwave hybrid heating, some kind of susceptor is there, and
Yes, sir.
susceptor is,
Rechargeable.
yes, and susceptor is something which absorb the microwave very rapid rate. So
Yes, sir.
whenever it absorb the microwave rapid rate, it get heat and it transfer their heat to the another contacted material.
Yes,
So
sir.
the
Yes.
generally the charcoal is used most of the time, the in order to process the metal. Can I Google in order to make you more clear? I think you
Uh,
I would get the my
okay. Fine, sir. Fine. I will contact directly, sir.
no. I would like to answer this question. So sorry, sir. So are you able to see this image? Susceptor particle. This image I think smaller, but are you able to see or not? Hello, hello,
Yes, sir. I am able to see.
hello, Bansal sir. Yes, so
Yes.
here the susceptor particles are there and microwaves are coming, and these microwaves would interact with this susceptor particle first, and after that the transfer heat transfer takes place with this substrate. Most of the time the material having high processing temperature is used microwave hybrid heating. But in case of polymer, that don't have that much processing temperature, that's why direct heating can be also used. But in case of hybrid heating, the losses are lesser and we can utilize the microwave fully. So
Sir, since the
this
heating is
is all
through
about.
conventional mode here, since the sir heating is through conventional mode because the charcoal is transferring its heat to the
Yes,
contacting material.
yes,
So, how would we
yes.
say that this is microwave heating? Because this is the material
That's
is getting
why.
heat.
Yes. Yeah, that's why it is known as microwave hybrid heating.
So
Because
there is a
some things is done by something is done by the microwave mode, and after that the conventional mode or the that conduction mode, the heat transfer is takes place.
okay, fine, sir, fine. Fine, sir. Thank you, sir. Thank you very much.
Thank you, Bansal. Thank you, Professor. Thank you, Professor. Thank you. Thank you so much for inviting me here. Okay, sir. Okay, okay.
Good night,
So,
sir.
so good night, everyone. Good night, Professor. So can I disconnect? Okay, thank you.